So now what we have that if we consider H epsilon V epsilon, then the terms of the order 1 divided on epsilon disappears due to choice of the function of the first character, choice of the function kappa 1, and we have the term of the order epsilon 0 for the constant. And what we have here? We have, of course, the derivative in t, the function u x at point x epsilon, plus the same what we already have for this operator, for this integral operator. We know that it is some effective matrix times on u at point x epsilon t, because now we consider the shift on b divided on epsilon, plus something small, plus small error, which is a function of x and epsilon x and t. So what we can write, how we can write this equation? We write this equation as follows: then h epsilon v epsilon xt is equal to h0 u at point x epsilon t plus something small. And again, in the same way as on our first lecture, we can prove that this error term tends to 0. So we obtain this relation. Now let us look how this relation help us to solve the main problem about the convergence of these two functions. Okay, let us write what we have. Just a second. Right here in this way. Just a second. So let us write our equation. So what we would like to prove? We would like to prove this convergence, right? Okay. So let us consider our problem, our limit problem. So we start with our limit problem, and first we consider the initial function as a function from the Schwarz space. Good. Then we can solve this problem, and we denote the solution of this problem. We denote the solution of this problem as function U0. There is a function. There is a function of x and t, and this function can be considered as the initial function for our ansatz. So we can construct the ansatz, let it be function v epsilon, as ansatz for function u0. Then, first of all, what we have for the function v epsilon. First of all, by the construction of ansatz, we know that v epsilon tends to u0 in our space. I will denote this space as infinity, the norm of infinity. So that means that I consider the space of the following function. So the norm infinity means that we consider the norm in the space of L2 function T, L2 T. And by our construction of ansatz, you can see there is function from L2, we already know. There is good function from the space, the Schwarz space in X, and smooth function in T. There is also, we know there is function in L2. So the norm of these two terms is small, so we can write that V epsilon tends to 0 when epsilon tends to 0. Great. But we are interested not V epsilon, but we are interested in the solution of this equation with operator L epsilon. And now let us compare V epsilon and U epsilon. So if we prove that V epsilon minus U epsilon in our space tends to 0, then of course we obtain what we'd like to get eventually. So the question, how to prove this convergence? Okay.
Shift.
Where is shift? Just a second. Shift is, of course, shift is here. Shift is, so we have, we don't have shift here, but we already have shift here. In ansatz, because in ansatz we already have shift. Yeah, ansatz is already with shift. Okay, and if we put now the function V to our operator H epsilon, then we have, using our lemma, that, just a second, that H epsilon, V epsilon is equal to H0 U0 plus V epsilon. But U0 is the solution of our problem. So H0 U0 is equal to 0. So we have this equation for V epsilon. Clear? Okay. There is important statement for us. And after that, let us consider, and again, and for function U epsilon, we also have the problem of the following way. U epsilon xt is equal to 0, right? So let us now consider the difference. Let us, I introduce function R epsilon, who is V epsilon minus U epsilon. And for this function, we have the following equation. The following problem. H epsilon, R epsilon is equal to phi epsilon, and R epsilon at time t equal to 0 is equal, let us look what we have here. We will, for V epsilon, we have function phi, yeah, plus something. And for function U, we have the same function phi. So the initial condition for our problem is some, okay, let it be some function psi epsilon, which depends only on x, and which has, again, the small norm. So the norm of phi epsilon and the norm of psi epsilon has the order epsilon. There are small norm. So for our function R, which is a difference of these two functions, we have the following problem. And we'd like to estimate the norm of function R. And there is linear problem, so let us consider two problems. First, when there is 0 here, and the second, when 0 is here, as usual. Okay, let us consider now a problem when there is 0. Okay, let it be first 0 here. Okay, good. And then we can write this, our problem in the following way. So we have, let me rewrite this operator like to this way. dt is equal to L epsilon R epsilon and plus nothing, but we have some initial condition psi epsilon. So what we can do, we can multiply our equation on R epsilon and on function V0 x divided on epsilon. So we know that this function, it is the same function as on the top of my desk, and I consider just periodic continuation of this function. And then we integrate in the limit on t, in the limit from 0 to some finite t, and in d psi over the torus, right? Not on the torus, but no, in AD, sorry, in AD, dx. Sure. And then we obtain the following. So what we have here, we have integral r epsilon square v, let it be v0 epsilon. I write it in this way. dt, so okay, maybe I write here 1/2 t is equal to 0, t is equal to t, and we should integrate over dx, right? xt x. So from on the left hand side we have this one, yeah? And what we have on the right hand side? Yeah. What? It is square.
No, R epsilon square. Square of R epsilon.
Yes. And what we have here? We have here integral over dt, integral over rd, L epsilon R epsilon, R epsilon, V0 epsilon, x dx. So x. I can write this integral as some quadratic form, yeah? I can write it like quadratic form associated with my operator, non-symmetric operator, L epsilon, R epsilon V0, right? And the very important technical moments, very important statement here, that this quadratic form can be estimated as a non-negative function. It is the main point in this estimate. So in some sense, we can symmetrize our function with help of this ground state, V0. So we don't consider symmetric function. But it is very important technical moment. So, but maybe if someone interested, I can explain later, but it takes some time to explain this fact. And so eventually what we have from this fact, it means that we have here estimate like to this one, and that means that we can estimate the norm of function R epsilon at point t, in fact at any time t, using the estimate on the function R epsilon at initial point. But we know that initial function is small enough. So from this estimate, we have the following, that the norm of the function R epsilon at time t. I write here any t from 0 t. V0 1/2, yeah, is less than r epsilon at time 0, which is psi epsilon, right? Psi epsilon V0 1/2. But we know that this function is strictly positive. It is bounded from below, from above. Then we conclude that the norm of this function is can be bounded by the norm of the function phi epsilon, but it is just some constant times epsilon. Okay. So it is small, and it tends to 0 when epsilon tends to 0. And the same, the similar arguments also can be applied in the situation when we have 0 here and we have some function as additional term, but with small norm. It is the same argument which are based on, again, on this estimate, very important estimate for us. So eventually what we have, we obtain that this function at any moment of time can be estimated with some constant. Of course, the constant can depend on t, but if we consider t on a bounded interval, then of course we can choose constant depending on this t large. And we obtain that the norm of the function r tends in our space for any fixed t tends to 0 when epsilon tends to 0. So that means that the difference between these two functions is small, so eventually we have that function u epsilon and u0 small.
Oh, it's all large of epsilon,
For this function, yes, I think so. I should check, but in any case, it tends to 0, for sure. I'm not sure about the order. Yeah, and so we prove this for our problem with initial function from the Schwarz space, and again using arguments that there is a dense space in L2, we can extend this result for the function in L2. So we prove the main theorem. Great. And finally, maybe very short, interesting consequence or just remark about so-called Einstein relation. It is some partial case. It is some partial case when the kernel, when the non-symmetric kernel has a special form. Let us assume that we consider.
That's good. This is what I was sort of asking.
So we have symmetric kernel, and we construct a non-symmetric kernel in a special way. So we start with this symmetric kernel and consider some small perturbation of non-symmetric kernel of the following form. So Z times A symmetric. So it is antisymmetric, and maybe we should just do some restriction. Yes, it is important that it is the same structure. So in some sense, there is some small antisymmetric perturbation on, in the scale of symmetric kernel, and L is a small parameter. So we consider really small perturbation. L is vector, L is vector from RD.
And who is omega p?
There is some truncation function, because we really would like to consider some truncation. Actually it is not so important, because and if to consider the corresponding homogenization problem for this kind of convolution, for this convolution, then again we can calculate the effective drift, and then the result, the Einstein relation, is the following.
And no conditional mu.
Mu should be symmetric. Again, it is bounded from below and from below, and mu symmetric. Psi eta, mu eta psi. Yes. Yeah, and the same problem, yeah, with convolution, which has this form. Then, if we consider the matrix which is defined by derivatives of this drift of the efficient drift, dbi dj over L and at point L equal to 0.
Over DL, no?
I'm
Over
surprised.
DL.
DL, yes, DL, yeah, sure. DLj, then 1/2 we consider, then it is exactly the effective matrix for symmetric problem. For symmetric, for non-perturbed problem. So in fact, that means that how to calculate, for example, this effective matrix, because it is really a very difficult problem. Then you try to organize some shift in a special direction and calculate the derivative, and then you can.
But why this is so, how do you call it?
Einstein relation, because as I know, it was first observed by Einstein. He considered some.
Yeah, the relation to what?
Maybe you explain, because you're expert in this.
Disordered systems.
Einstein.
And Einstein, yeah, and in 2 papers, one was published in the very beginning of his career, and second at the very end of his career. He expressed in the following way: if we have some disordered system, and we imply small forces, then the reaction of the system on small forces is proportional to the effective diffusion of non-perturbed system. And he called it mobility. The reaction of system, small reaction of system on small forces, he called it mobility of the system.
I never thought.
You mean this exactly this term, yeah? Mobility,
yeah.
mobility.
Disordered
Yeah, because otherwise, how to calculate this effective matrix? I remember that it is also related with some gravity models of gravity.
He studied, he expressed it for generic disordered system.
Yeah, so.
Yeah.
Yeah, and by the way, yeah, in this non-local situation, it works.